There are some stories in science we all think we know. The Michelson-Morley experiment is one of them. It's the experiment that failed so spectacularly it led to Einstein and relativity. Case closed, right? Well, what if the answer we all learned in school missed something? Something deeper and, frankly, a lot stranger. A geometric truth about the very fabric of reality itself? Okay, so let's dive right in. Picture this. It's 1887. Physicists are pretty sure that light needs something to travel through, right? A mysterious invisible substance they called the luminiferous ether. So as the Earth is barreling through space, it should be creating a kind of ether wind. And this experiment was designed to do one thing: measure that wind. So they set up this incredibly clever device, an interferometer. It splits a beam of light, sends the two halves down different paths, and then brings them back together. Simple enough? The idea was that the ether wind would slow one beam down just a tiny bit, which would create a very specific, predictable shift in the final pattern. But when they ran the experiment, what did they find? Absolutely nothing. Zilch. A big, fat zero. And this is where it gets kind of mind-blowing. Look at the scale of this failure. They were expecting a shift of about 0.2 fringes, but their instrument was so ridiculously precise, it could have detected a shift 20 times smaller than that. We're talking 0.01 fringes, and yet the measurement came back as nothing. It wasn't just a small result, it was no result at all. So this null result just completely broke physics. It was a crisis. And it's this crisis that famously paved the way for a young patent clerk named Albert Einstein. He came along and said, hey, maybe the problem isn't your experiment. Maybe there is no ether, and the speed of light is just constant. And boom, you get the theory of special relativity, which stretches and squeezes time itself. But what if that wasn't the only way to explain it? See, the standard story we all learn jumps straight from the failed experiment to Einstein. But in doing so, it glosses over a really subtle but absolutely profound assumption. It's an assumption we all make every second of every day without even realizing it. And it's all about the simple idea of now. This right here, this is the question at the heart of it all. When we look at that experiment, we just assume we can define a single, universal now across the whole setup. But how can we really be sure? How do we know that the moment a photon hits a mirror way over there is truly happening at the exact same instant as something happening right here? We basically treat reality like it's drawn on a piece of graph paper, right? A flat, rigid Cartesian grid, where at the same time just means two things line up. Now, Einstein challenged that by making time relative and stretchy. But this alternative model we're exploring today challenges something even more fundamental: the idea that space itself is flat. So this leads us to a pretty wild alternative. Instead of explaining that null result by messing with the rules of time, what if we change the rules of space? What if the flat space we experience in our labs in our daily lives is actually just a projection, a shadow of a curved surface that exists in a higher dimension? And this slide just lays it out perfectly. You've got two paths to the same answer. Special relativity says space is flat, but time is flexible. This new model says time is more rigid, but the space we perceive is actually a curved, complex geometry. The solution isn't in the clack, it's in the ruler. This idea is called the spherical cap model. I know, it sounds pretty out there, but stick with me. It suggests that our flat, 3D world is basically just the surface of a cap on a sphere in a higher dimension. And in this bigger, truer geometry, two events are simultaneous, not because they share a moment in time, but because they are the exact same true distance from you, the observer, through this higher dimension. Kind of like how every point on the equator is an equal distance from the North Pole. So how on earth can we wrap our heads around something like this? Well, the best way to do it is to look at the experiment through three different sets of eyes. These three observers help us see how our version of reality gets built, layer by layer. Okay, so you can see here our reality is constructed in layers. First, you've got the participant. This is the observer who is inside the experiment, moving with it, experiencing everything firsthand. Then you have the analyst. This observer is sitting still, watching everything happen, and trying to reconstruct a flat map of what went down by calculating for all the light speed delays. But there's a third, final layer, the geometer. This observer sees the ultimate truth from a higher dimension. They can see that the analyst's flat map is just a projection, a shadow of the real curved geometry of the spherical cap. Here's a great way to think about it. The analyst, our second observer, is like an ancient cartographer trying to draw a flat map of the Earth based on sailors' reports. They have to make all these funky corrections and distortions to make it work. But the geometer, the third observer, is like an astronaut looking down from orbit, seeing what's really going on. It's not a distorted flat map, it's just a globe. All right, so we've got this strange new picture of reality. But how does it actually solve the original puzzle? How does this whole spherical cap idea explain the Michelson-Morley experiment's bizarre null result without needing to stretch time like Einstein did? Honestly, the explanation is incredibly elegant. It's all about the true path the light takes. In our flat view of the world, one path for the light beam looks longer than the other. But remember, we're not on a flat map. We're on the curved surface of this cap. And on that curved surface, what looks like a longer path is actually a kind of geometric shortcut. The delay you'd expect from the Earth's motion is perfectly, and I mean perfectly, canceled out by the curvature of space itself. The two light beams arrive at the exact same time, not because of some weird timey-wimey stuff, but because on the real map of reality, their paths were the exact same length all along. And that really is the most powerful takeaway here. To solve that baffling puzzle from 1887, Einstein's special relativity gave us a reality with flexible, stretchy time. This spherical cap model gives us a reality with a flexible, curved space. Two totally different explanations that both lead to the very same experimental result. And that leaves us with one heck of a final thought to chew on. If our straightforward, flat reality, the one we touch and see every day, is really just a projection of a deeper, curved, more complex geometry, like a shadow on the wall of Plato's cave, well, it makes you wonder, doesn't it? What other fundamental truths about our universe are hiding just outside of what we're able to see?